We have seen water in our solar system. The truth is a harsh contrast to what many of us were taught years ago about Earth being so unique in that way. There's water on every planet, in many of the moons, often in great abundance. It's on our star. It's in sunspots. It's around every star we see, around what the mainstream describes as black holes, and even on alien worlds. We've learned that the solar wind carries every known element, and that CMEs increase the density of the solar wind dramatically. We know that some of the hydrogen gets past Earth's magnetic shields. We know our planet releases oxygen during CME impacts from way up in the upper atmosphere, in the electric layers. We've seen how Earth's oxygen and the volume that erupts, combined with our relative proximity to the Sun, could mean that we had just the right chemistry for minuscule water delivery over billions of years, a better setup for potential electrochemical H2O combination right above our heads. But we also know that rogue comets, asteroids, and planets can contain a lot of water as well. We even see water-rich planetary nebulae light years across. How do these areas out in space get their water? In the pre-stellar and pre-planetary nebulae, we can't blame comets or even stars. By now, it's popular knowledge that we can use slight light disruptions to determine when a planet passes in front of a star. And now we're finding rogue planets in this way. We know that rogue planets have tremendous ability to contain water, because we often see them born free of any star from those very same water-rich masses, the planetary nebulae. Little dense projections called globulettes. These dense molecular clumps, as the scientists describe them, will eventually condense into planets. Most lack the requisite mass for stellar potential. So these planets are sentenced to a long time of loneliness as they scatter about through the galaxy. Speculation about the great abundance of rogue planets quickly turned to near certainty. Rogue planets outnumber stars in our galaxy. Experts are estimating they could be double the number of stars, or more. And if true, that means there's more than a 50% chance of there being a rogue planet closer to us than Proxima Centauri. Coming back to the question of where they got their water. Sure, stars pump out the ingredients, but what about massive pre-stellar and pre-planetary nebulae? You know, the ones with bits rich in water that end up on rogue objects without a home. Well, one potential mechanism for this huge water delivery to relatively condensed areas is a cosmic jet. We already know stars can shoot water bullets. The polar jets from stellar and galactic centers can span dozens or thousands of light years respectively. The same solar wind particle distribution applies here, and one would have to imagine a similar electrochemical reaction causing combinations of atoms into things like water would have to agree with this situation. We have recently learned that the difference between a stellar jet and the jets from galactic centers really isn't much of a difference. We find those same heavier elements amidst the charged particles in those galactic jets. So why should the water formation mechanism not apply there as well? One can only imagine that that's the next thing to be confirmed. And the most likely place for that confirmation will be from our very own galaxy. We have detected the long-faded jet from our own galaxy, like a shadow of its younger self, but not dead by any means. The theme here is that these massive celestial objects not only eject all the ingredients, but they do so in mass from their polar jets, not just in their youth, but throughout their lifetimes and the life of their systems. We must also consider more localized and relatively significant mass deliveries of water, say on a solar system or planetary scale. These massively abundant rogue planets go traipsing through space, often spending eons in relative isolation. But as nearly certain as the majority live lonely lives, there is a similar certainty that some will eventually catch a star in the crosshairs of its trajectory. Now, while the brightness of such a star grows, and the distance between rogue planet and star dwindles, an interface boundary will be approached. Just as Earth has a protective magnetic field, so do stars. We call the shield of our Sun the heliosphere, and while it protects against cosmic radiation, it does about as much to stop these solid bodies as Earth's shield does to stop meteors from falling. But beyond the electromagnetic interface, an outer shell known as the Oort cloud can be found. There is a modicum of controversy over just what's out there, especially regarding the true nature of the comets alleged to originate in this region of space. But what is not in doubt is that this pseudo-shell of solar systems appears to be the place where the solar wind slows down and congeals all those ingredients. We know there are a lot of larger rocky bodies out there in that region of space. Many would be nearly impossible to be missed or unperturbed by an intruding object of any size. So what exactly is out there with them? There's a good deal of rock, like the asteroid belt, but there's a lot more. Consider the magnetic fields of the Sun. This simple magnetic form extends out past Pluto to where the solar wind stops. Much of the charged particles expelled in the solar wind and polar jets would obviously follow the magnetic channels naturally formed by the stellar fields and be in great abundance at the outer stellar shell, enduring constant combination potential. That means more gases, hydrogen, free oxygen, nitrogen, and other elements we often find locked up as solids in rock form. There is no doubt it's possible for a rogue planet to miss a star and all of its planets by a wide margin, and yet still have the magnetic, gravitational, or even kinetic interaction with those outer shell bodies to potentially send objects hurtling into their inner systems. We have seen undeniable proof. Stars, including our Sun, are pumping out a broad scope of elemental mass. We know that Earth's chemistry offers an explanation for it having so much more water relative to the other planets, but it's also certainly possible that such a rogue planet or cometary mechanism chose a lucky planet or two along the way, perhaps Earth, or perhaps more likely, it acted in concert alongside the stellar delivery methods that we've already described in chapters 1 and 2. It's likely been many years since something like this has been seen from the surface of the Earth. Recent spectral emission lines from Oort cloud comets reveal startling amounts of carbon compounds and variously saturated nitrogen compounds alongside the water suggested in the dirty snowball theory of the mainstream science. Did something like this make a major contribution to Earth's abundant water? It's one of many unanswered questions. You don't even need a rogue planet for such a localized, planetary delivery event. Deep in the dark outer regions of our own solar system, a number of trans-Neptunian objects are found in often eccentric orbits amidst the outer shell regions that we call the Oort cloud. Xenia, Sedna, even Pluto, they're out there, potentially impacting or perturbing smaller objects. Nobody can say for certain if this has ever caused a comet to have major effects on Earth, but the possibility is as real as the oxygen erupted by Earth's ionosphere to meet the hydrogen of impacting CMEs. Scientists at the Harvard-Smithsonian Center for Astrophysics purport that rogue planets can actually be captured by stars. Who's to say that such a thing has not happened at our own solar system? In fact, there are some who purport that just such a thing may have happened. I will simply say that my world was turned upside down by David Talbot and the Thunderbolts Project in a video called Symbols of an Alien Sky. On the website page for these StarWater videos, that video will be embedded with my highest watching recommendation. 3 chapters down. Lots of water. Lots of ways to get it, lots of ways to give it. In the final chapter of StarWater, we will examine the latest Kepler data and apply the conclusions drawn from the preceding chapters to communicate a groundbreaking reality about our universe.